This is part B for our study guide and review of the vessels. So just as a recap, we have multiple mechanisms to stimulate and regulate some of that blood flow in vessels, and that is autoregulation. We have neural, and we have endocrine control. So we talked about autoregulation in the previous slides. Now we're going to move on to the neural mechanisms as to how it is that we control the cardiovascular center. So remember that we have the cardioacceleratory center to increase cardiac output and the cardioinhibitory center that reduces cardiac output. The vasomotor center within the brain will exert sympathetic control, and that is with an increase on epinephrine, and that is short for epi, all right, over those vessels to change blood vessel diameter. So remember that we have our blood vessel, and within that tunica media we have alpha receptors, and those alpha receptors within that smooth muscle, as soon as epi is released into circulation, it will activate these receptors, allowing that smooth muscle to contract. And when there is contraction of that smooth muscle, there will be vasoconstriction. And when we cause vasoconstriction, we are now redistributing blood flow to specific sections of the body, depending on whichever response we want to stimulate. When we're talking about sympathetic response, we're talking about a fight or flight response. So let me just erase this. When we're talking about a fight or flight response, you are trying to increase vasodilation to those muscles that are crucial to the escape or the fight, and that is going to be skeletal muscle, right? So we're going to increase blood flow to these areas, to your muscles, to your legs, to your heart as well. And we're going to decrease blood flow to the kidneys. We're going to decrease blood flow to your GI tract. You don't need to digest or to process food at that time. We're going to decrease blood flow to the skin. More so, we're gonna then, constrict blood flow to these areas, and we do this by the activation of alpha receptors, and the smooth muscle that is vasoconstricting is restricting blood flow to these areas, and instead we're vasodilating the vessels within the muscles. So by stimulating beta receptors within muscle, and that is a skeletal muscle, we're vasodilating. So when we look at the hierarchy of action, remember that we have epinephrine being released during that fight or flight response. And that epinephrine will have different actions depending on the tissue that is acting on. So if we're talking about vessels within the muscles, we will have a beta receptor activity causing vasodilation to these vessels. So we're increasing blood flow to muscles. We're increasing flow. And when we are having epinephrine activity on vessels of the skin, the GI tract, and the kidneys, we're causing vasoconstriction. All right. Overall, our our sympathetic response is gonna cause more vasoconstriction to more tissues, and we're gonna change vessel diameter in different types of tissue. So our increase on sympathetic stimulation, most of the body is gonna undergo vasoconstriction, and when we have a decrease on that sympathetic expression, we're gonna have decreased sympathetic stimulation, and that is gonna cause those vessels to change in size. So again, if the epinephrine is being released, epi is being released, It's going to have different action in different tissues of the body. In a skeletal muscle during that parasympathetic is going to cause vasodilation, and we're going to increase blood flow. But in other tissues, it's going to cause vasoconstriction, and that is because we're now restricting blood flow to these other areas, and we're now shunting blood flow to those muscles that are needed for fight or flight. As we decrease this fight or flight response, so if we decrease epinephrine, then there will be less vasoconstriction in these areas, and blood flow will naturally restore to these areas. All right, to the kidneys, to the GI tract, into the skin, and the muscles will go back to that resting state. So there will be less flow going to these areas. So as a recap, we have different mechanisms within your body to increase blood flow and redistribute blood flow as needed. One of them is neuronal, and that is with the neuroendocrine mechanism. With neuroendocrine mechanisms, we can redistribute blood flow as needed. Now, if the autoregulation is ineffective, and that is that through capillary vasoconstriction or vasodilation, we're unable to supply blood, or we're unable to provide enough oxygen to this tissue right here, and we'll go with a we'll try to show a capillary bed. If we're unable to restore or provide enough oxygen to this tissue right here, then we need to increase blood flow to this capillary bed. And let's think about this is a muscle fiber within the leg. So during a fight or flight response, we need to increase blood flow. How do we do that? There will be an activation of the cardiovascular center, and we'll start releasing molecules such as epinephrine. And when we do that, we're now vasoconstricting the periphery so that we can redistribute and we can cause an increase in flow to this type of tissue, and we're vasodilating the vessels that are feeding this muscle. All right. This type of action is short-term lived. This epinephrine, it is metabolized very fast, so this is more so for short-term action. A longer way to increase cardiac output through your body will be through endocrine systems, such as your kidneys. When the kidneys are receiving less perfusion and they are unable to receive less perfusion, we have a release of hormones that then act on themselves to increase blood volume and therefore increase blood pressure. And this is to restore homeostasis and increase blood flow to the areas that are needed. Okay, so just remember that we have different receptors within blood vessels to react and to monitor flow to the different areas of the body. We have baroreceptors, which basically are monitoring blood pressure, and they react based on blood pressure changes. We have also chemoreceptors that respond to chemical composition changes. So if there is an increase in CO2 or an increase in oxygen, these chemoreceptors will react accordingly to adjust flow to that capillary bed. Alright, so for baroreceptor reflexes, remember that we're talking about carotid sinuses and aortic sinuses. So these are monitoring changes on blood pressure. Whenever there is a stretch of that vessel wall, there will be activation of this type of receptor. So carotid sinuses maintain blood flow to the brain. When there is a decrease in blood flow through the carotids, they will constrict. So decreased flow will cause vasoconstriction in order to redistribute blood flow to that section of the brain. All right. The aortic sinuses are monitoring blood flow to the systemic circuit. So systemic circuit. Oops. Sorry about that. So with these, we're trying to make sure that the organs throughout your body, such as your kidneys, are well perfused. So again, baroreceptors are monitoring blood pressure changes in blood pressure, and this is through vessel wall stretching. So when the vessel wall is stretching, it will activate or decrease activation of the baroreceptor. When we talk about baroreceptors, there are two types. We have the aortic sinuses and we have the carotid sinuses. Now, the aortic sinuses are in charge of controlling perfusion to the systemic circuit, and the carotid sinuses are controlling blood flow to the brain. So as we picture, there is this vessel, and we have our baroreceptor within that vessel. When we have an increase in blood pressure, there will be more pressure going through this vessel itself, and there will be more force pushing that vessel, stretching that vessel wall. When that happens, there will be an increase in baroreceptor input to the vasomotor center. So the vasomotor center within the brain, all this is going to send signals to the vasomotor center in the brain, and it's going to tell it, hey, look, our blood pressure is really high. We can now start decreasing that sympathetic activation. Sympathetic neurons are inhibited and they release more or less norepinephrine. We will reduce less norepinephrine. So when we have less norepinephrine, there will be a decrease of vasoconstriction in the periphery, and there will be less redistribution of blood flow to the brain. All right. This causes peripheral vasodilation. Vasodilation, remember that it is just the lack of sympathetic stimulation which causes blood pressure to decrease. All right. So as we have, if we picture this person right here, and we have a fight or flight response, how do we increase a fight or flight response towards the end of that fight? We want to increase blood flow to those muscles. So we're releasing norepinephrine, all right? And that norepinephrine is going to cause vasoconstriction on the kidneys, the skin, the GI tract, throughout that periphery, and is now going to shunt blood to those muscles. And now that it has blood flow to those muscles with the action of norepinephrine, there will be vasodilation with an increase in blood flow. So again, norepinephrine will cause vasodilation in the muscles, and it will cause vasoconstriction in periphery. And that is like the skin, like your kidneys. But we're able to divert blood flow to the muscle because there is less of we're shunting blood away from those non-essential organs for fight or flight. But when we are doing that, we're increasing pressure, and that pressure will exert into the vasomotor center a signal that is long term. And then the vasomotor center will decide, well, now that we've achieved that we're not on a fight or flight response, we can decrease norepinephrine. And when we decrease norepinephrine, eventually, then the decrease in norepinephrine will cause vasodilation by the lack of norepinephrine that is on the body, and everything goes back to a normal state. This will cause the blood pressure to be decreased because we don't need increase perfusion to those muscles. So again, baroreceptors are monitoring changes in blood pressure. When blood pressure rises, there is increased baroreceptor input to the to the vasomotor center, telling it that we need to decrease epinephrine activity. So it inhibits sympathetic neurons to decrease norepinephrine. This is going to cause vasodilation, and when we cause vasodilation in that periphery, then we're allowing the body to accumulate more blood, and there will be a decrease in blood pressure. As blood pressure falls and there is decreased baroreceptor input to the vasomotor center, let's say for instance we're now going down to the point of a too little norepinephrine, there will be too much vasodilation. So now those receptors, baroreceptors, are going to send too little input to the vasomotor center, and it's going to cause sympathetic neurons to release norepinephrine to cause vasoconstriction and increase blood pressure. Remember that we're talking about a homeostatic state. So your body is constantly checking, making sure that the blood pressure is adequate to perfuse all the other organs, such as your kidneys, your lungs. So we may increase or decrease despite of a fight or flight response to keep enough perfusion to those organs. I just wanted to take a quick second to go over the big picture here, and that is that we have the cardiovascular center in the brain, and that is in the medulla oblongata. So we have this center within the brain, and this is further divided into two portions, and that is the cardiac center and the vasomotor center. When would you think of the cardiac center, then you can divide it into two sections, and that is the cardio-acceleratory or the cardio-inhibitory center. It is within this, the cardiac center, that we are adjusting force of contraction of that ventricle. We're also adjusting heart rate to increase blood flow or decrease blood flow, and this is going to affect blood pressure. The vasomotor center is going to affect vessel tone to help with blood redistribution. Blood redistribution. Alright, so whenever we're trying to increase or decrease blood, we're going to send signals to the cardiovascular center, and we're going to have different effects from each one of these, the cardiac center or the vasomotor center. So here we talk about a state of homeostasis with normal blood pressure. And as blood pressure is disturbed and there is a rise in blood pressure, there is going to be an increased input from baroreceptors to that cardiovascular center. That cardiovascular center, again, we divide it into two sections. The cardiac, we're going to put in here cardiac, either be cardio-inhibitory or cardio-acceleratory, and we have also the vasomotor center. All right, now since we have an increase in baroreceptor stimuli, we want to tell the cardiac center to decrease the stimulation. So let's go through that cycle first. We're going to have a cardio inhibitory response, and we're going to have decreased cardiac output with decreased force and decreased heart rate, and that is going to lead to a decrease in blood pressure from this side. And the center is also going to have a vasomotor response, where we're now causing vasodilation in the periphery with decreased norepinephrine. When we have decreased norepinephrine, then there will be less vasoconstriction in the periphery, and we will redistribute blood flow to that periphery, and we will lower blood pressure until we get to this homeostasis. Let's go through the opposite exercise. So if we have a homeostatic state, and from that homeostatic state we have a decrease in blood pressure, there will be less input from those baroreceptors, sending a signal to the cardiovascular center. And as we take a closer look, we now divide these into two sections. We have the cardiac center, which divides into the cardioacceleratory and the cardioinhibitory, and we have also the vasomotor center. So let's take a look at the response from each one of those. Because we have a decrease on input from those baroreceptors, we want to increase blood pressure. So we're going to stimulate the cardioacceleratory. That cardioacceleratory is going to release epinephrine to the heart, and it's going to cause an increase in heart rate and an increase in force of contractility. Now, from a vasomotor center, because we have a release of norepinephrine, all right, we're going to have a vasoconstriction, and that vasoconstriction in the periphery is going to shunt blood to areas that are needed, such as the heart, and that is going to cause an increase in blood pressure overall. Now let's take a look at the chemoreceptors. The chemoreceptors, we say that they are responding to changes on chemical compositions within your blood. So these peripheral chemoreceptors are specific to carotid bodies, aortic bodies, and monitor these are monitoring arterial blood flow. So the carotid bodies will be located in the neck, in the carotids. Make sure that we highlight these. And we have the aortic bodies which are located near the aortic arch. There are some central chemoreceptors in the brain itself, and these also will stimulate different receptors. They're monitoring composition of the CSF. So let's go over chemoreceptors. Chemoreceptors monitor the chemical composition of arterial blood at specific sites, such as carotid. Are we talking about sinuses or bodies? Make sure you know the difference, because bodies are referring to chemoreceptors and sinuses refer to baroreceptors. We're talking about aortic bodies, and there is another type that is specific to the brain within the medulla oblongata that is monitoring the CSF, the cerebrospinal fluid chemical composition. So when we're checking this composition, we're checking for multiple levels. We're checking for oxygen, we're checking for CO2, we're checking for pH. Those are the three main ones. So when there is an increase in CO2, we call that hypercapnia. Okay, it's a retention of CO2. There is a decrease in pH, which we call acidosis. Remember that pH level, when it is below that range of 7.35, we deem it acidosis. And there is a decrease on oxygen, which we term to be hypoxia, when you are below that 90% O2 saturation. Then we are stimulating, we're sending a signal to that response to the cardiovascular center. And when the cardiovascular center, remember that we have the cardiac center and the vasomotor center. And within the vasomotor center, we're going to have a change in within the cardiac center, we're going to have a change in blood pressure. We're going to have a change on heart contractility and heart rate. And from a vasomotor center perspective, we're going to have a change in vessel diameter. So as we have a change, we have an increase chemoreceptor input. Let me just erase that and write it right. When we have acidosis, hypercapnia, hypoxia, there is an increased chemoreceptor input to the vasomotor center. So we're increasing it. And that is going to cause sympathetic neurons, so it's going to cause a cardioacceleratory response. They release norepinephrine. This is causing vasoconstriction in the periphery to increase blood flow to the areas where we need to increase it, such as your brain, and it's also going to affect the respiratory center as well in order to modify those gases. We'll review these in the respiratory center. Now here they release more norepinephrine because we have a cardioacceleratory response. In this picture we have a response to acidosis, hypoxemia, and hypercapnia. So we have an elevated CO2, we have a decrease on oxygen, and we have a decrease in pH. All right. When we have all of these, there is going to be an activation of those chemoreceptors where there is going to be an increased signal to the cardiovascular center. The cardiovascular center is going to have two portions, the cardiac, and it's going to have the vasomotor center. The one that ends up being activated in this section is going to be the cardioacceleratory itself instead of the cardioinhibitory, because we need to increase cardiac output to increase blood flow to your heart as we're trying to mobilize blood flow and increase oxygen levels. So we want to increase blood flow to the lungs and to the kidneys to restore pH. We're also affecting the respiratory center, and that also helps restore some of that homeostasis within those blood respiratory gases. When we look at the vasomotor response, we're causing vasoconstriction to increase blood flow, and all of this is going to increase blood pressure to restore homeostasis. So just as a review, in cardiovascular regulation, we have epinephrine and norepinephrine from the adrenal medulla. This is causing vasoconstriction in the periphery. And when we increase vasoconstriction in the periphery, we're shunting blood away from the skin and moving it towards the vital organs, such as your systemic circuit, and this is going to increase blood pressure. Coronary vasodilation will be increased because remember that these two molecules are having action on different receptors on different tissues, on muscles and heart. We have beta receptor activity, which means that when we release epinephrine and norepinephrine, we're activating this and we're causing vasodilation. And when we're releasing epinephrine and norepinephrine to the kidneys, to the skin, to the GI tract, we rather have an overabundance of alpha receptors. So those tissues, when you release epinephrine, are going to cause vasoconstriction. So you are trying to shunt blood away from non-vital organs to vital organs, all right, for fight or flight. But overall, we're increasing blood pressure. Another, hormone that is released is the kidneys. The kidneys are produced due to a decreased blood pressure, and this angiotensin II, it is aimed at increasing blood volume, and if we have a higher blood volume, well, we're going to have a higher cardiac output. So this is a potent vasoconstrictor and is going to increase blood pressure, and is going to cause the release of aldosterone, antidiuretic hormone, and these two are going to promote fluid retention to increase that blood volume. This molecule is working within the kidneys to increase some of that fluid retention to increase cardiac output. So key takeaways here, we have neural and endocrine responses. Neuronal responses are either sympathetic or parasympathetic. And the sympathetic and parasympathetic responses are short-term lived. The endocrine response is longer lasting. This endocrine response is aimed at changes in blood volume. In blood volume. This neural change is aimed at changes in the cardiovascular center in the brain, which then therefore affects the cardioexcitatory, cardioinhibitory, and a vasomotor center. Now, let's take a look at what happens when there is a decrease in blood pressure or a decrease in blood volume. Epinephrine and norepinephrine are released by the adrenal medullas as hormones, and they are causing vasoconstriction, which in turn are increasing blood pressure because they're trying to redistribute blood flow. Renin is released by the kidneys, and this renin leads to the production of angiotensinogen 2. Angiotensinogen 2 is produced by a couple of ways. So here that brings us to the next portion, and that is how do we produce angiotensinogen 2. Angiotensinogen 2 is created because we have our liver, and our liver is producing angiotensinogen. So angiotensinogen is free flowing in circulation, is produced by your liver, and is waiting to be activated. When there is a decrease in your blood pressure, the kidneys release renin, and renin then goes on to convert angiotensinogen into angiotensinogen 1. Angiotensinogen 1 then goes on to be converted by angiotensinogen converting enzyme, short for ACE, into angiotensinogen 2. Now this angiotensin 2 is going to cause 3 different ways in which we can increase blood pressure and increase blood volume. So we're going to cause vasoconstriction. It's going to cause vasoconstriction so that we can increase blood pressure, so that we can increase that flow to the vital organs. All right. We're also going to cause an increase on antidiuretic hormone, which is going to cause an increase in water retention. We're going to also increase aldosterone, which is going to help retain sodium so we can retain blood, retain water. So if we retain more water and we are reducing the elimination of water, then we're going to increase blood volume. In short, angiotensin 2 causes the release of antidiuretic hormone and aldosterone to increase blood volume. You should know what each one of them do. Aldosterone increases sodium retention, and with that we retain more water, so we don't eliminate it through the kidneys. And antidiuretic hormone prevents the removal of water, so it reduces urination. Aldosterone also causes thirst, so with that you are thirstier and then you consume more water. We have our antidiuretic hormone is released by the posterior pituitary gland to decrease blood pressure or blood volume. Remember, this is an effect from activated angiotensin 2, all right? And this is helping increase blood pressure and blood volume because it promotes water retention, all right? And angiotensin 2 is also causing vasoconstriction. Let's take a look at this neuroendocrine response when there is a change in homeostasis. So we have our disruption of homeostasis with a decrease in blood pressure. Let's take a look at the short-term response through that a sympathetic response. When there is a short term, we have sympathetic activation, and we're releasing epinephrine and norepinephrine from the adrenal medulla. And when we have that, we have an activation of the cardioexcitatory center and the vasomotor center. So we're causing vasoconstriction in the periphery to increase blood flow to our organs, to our vital organs, and we're also increasing heart rate, force of contractility. So we're trying to restore blood pressure. All right, we're trying to restore blood pressure, and that is going to cause an increased blood pressure to try to restore homeostasis. Now, this is short-term lived, so if we need more of a sustained elevation in blood pressure, we now go through an endocrine route. Now, with this endocrine route, remember that we have angiotensinogen as just a plasma protein that is circulating in blood waiting to be activated. When we have that decrease on flow to the kidneys release renin, and this renin goes on to cleave angiotensinogen and convert it into angiotensin 1. Angiotensin 1 is then converted to angiotensin 2 by ACE, which is angiotensin converting enzyme. And it is this angiotensin 2 that goes on to cause the release of multiple molecules. And that is going to be antidiuretic hormone, aldosterone. Antidiuretic hormone is going to cause so that we eliminate less water, and with that we're going to have an increase in blood volume. Aldosterone is going to cause a retention of sodium, and with that we're also going to retain more water, and it's also going to make you thirsty. And when you're thirsty, you're consuming more water, and that is going to cause an increase in blood volume in order to restore homeostasis. So we took a look at that neuronal response to increase blood pressure. Let's take a look at the natriuretic peptides that are used to decrease blood pressure. All the previous hormones, again, were used to increase blood pressure, to increase circulation. The natriuretic peptides, on the other hand, act to decrease blood volume, and if we decrease blood volume, we're decreasing blood pressure. Muscle cells in the heart produce two kinds of peptides, and those are atrial natriuretic peptide and brain natriuretic peptide. The peptides are produced in response to excess diastolic stretching. So extra stretching when the heart is relaxed. This means that there must be too much blood flow into the heart. If you remember, we have our ventricles, and at the end of end diastolic, we look at our end diastolic volume. If this is increased, it's going to cause those ventricles to stretch, and when they are about to contract, they are less efficient. This is leading to the release of those peptides. These peptides are opposing antidiuretic hormone, and with that we are promoting water loss. Their effect is not within the sympathetic or cardioinhibitory center, but is mostly so through the release or the decrease of blood volume. So when we have an increase on blood pressure or blood volume, we have atrial and brain natriuretic peptides that are released from the heart. The AMP, atrial natriuretic peptide, or BNP, are causing a decrease, they're causing an increase on sodium excretion, increasing water release, water excretion. They're increasing sodium excretion and increasing water secretion. This is causing also vasodilation. The net effect is to decrease blood volume and to decrease blood pressure. Let's take a look at the homeostasis. We have a rise in blood pressure, making that end diastolic volume to increase. Now it is causing AMP and BMP to be released. This is going to antagonize or oppose antidiuretic hormone, and when we're doing that, then we're gonna cause an increase of sodium release through the urine. And when we have a release of sodium, we're going to have decreased water retention, and water is going to follow. We're also going to have more water secretion. It is going to reduce thirst. It's going to cause some vasodilation, and we're going to reduce blood volume overall to restore that rise in blood pressure.